Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is overload relays. Our objective is to take a brief look at overload relays. An overload relay is a sensory device that protects a motor from sustained excess current draw. An overload relay will allow a harmless temporary overload, such as an inrush condition during starting. However, will trip if current is high enough to cause motor damage over time. The overload relay can be reset once conditions causing the overload event have been detected and resolved. In contrast to a fuse or a circuit breaker that protects the motor from brief high current events associated with short circuits, an overload relay is used to limit current for a predetermined window of time. Excessive current may damage a motor by progressively breaking down the winding insulation. Motor overload conditions can occur if the rotor is locked, the motor is undersized for a given load, if the motor is frequently started and stopped, or if there's a loss of one of the phases in an industrial three-phase AC system. Additional causes might be under or over voltage, damaged bearings, improperly aligned shafts, poor ventilation, high ambient temperature, or a combination of these factors. An overload relay paired with a contactor forms the two necessary components for a motor starter, being 1, a means of starting or stopping the motor, the contactor, and 2, a means of protecting the motor from sustained overload conditions, the overload. The NEMA schematic symbol for an overload relay is a pair of opposing question marks each phase. The IEC schematic symbol for an overload relay is kind of a digital pulse each phase. The overload heater elements are placed in series with the contactor and the motor is intended to protect, and are rated to carry primary current. Note an overload relay also includes one or more pilot-rated auxiliary contacts used for feedback by the pilot ladder logic. We'll discuss the role of this feedback mechanism in a moment. An overload relay can be integrated with a contactor in a single package called a motor starter, or the pair working together can be considered a motor starter. Note the schematic symbol for a manual motor starter includes both the symbols for a circuit breaker and an overload. Here's a manual motor starter featuring a contactor paired with an overload element integrated into a single package. The manual motor starter can be turned off and then locked out and tagged out. Here's a magnetic contactor and a matching overload element. This combination working as a pair would be considered a motor starter. Note this three-phase overload element only has one heater installed. Each phase would ordinarily have a separate heater. Often overload relays have a carrier into which the overload relay snaps. The carrier and overload relay combination allow it to be tightly paired with a contactor for a motor starter. Other lectures discuss contactors and manual and magnetic motor starters. Again, an overload relay by itself cannot rightly be considered a motor starter since it lacks the means of establishing or interrupting high current delivered to a motor provided by the contactor. The overload's only purpose is to protect the motor from sustained overload conditions. Key to your understanding of overload relays is this simple fact. Overload elements do not ordinarily directly make or break connection to a high-power electrical load like a three-phase AC industrial motor. This is ordinarily the role of the contactor. Overloads are sensory and detection elements only, and feedback elements inside the control circuit tell the contactor to break connection when the overload senses a sustained overload. This is the reason a motor starter is formed of two elements. A contactor cannot detect sustained overload conditions, and an overload cannot make or break connections. However, the pair working in combination can both make and break connection and detect sustained overload conditions. The feedback from an overload relay ordinarily takes form of a normally closed contact in the pilot circuit that, when in the deactivated ready or go state, is closed. If the motor is operating under normal conditions, remains in the closed state. Current-sensitive thermal or magnetic elements inside the primary circuit, upon sensing a sustained overload condition, cause this contact to open, thereby de-energizing the contactor coil and opening the primary contacts. We'll discuss ladder logic implementation using overload contacts in later lectures. Most overload relays share some common features, principally a reset that can be toggled between manual and automatic mode, and an adjustable current setting. The manual or automatic reset means that after sensing a sustained overload condition, the overload may require manual acknowledgement to be reset, or after cooling, the overload will automatically reset itself. If an overload is accidentally placed in the wrong mode for a particular application, a dangerous condition could result. Overload relays with adjustable current settings allow the overload to be employed for a different range of applications. Some overload relays may also feature a trip indicator that gives a visual signal of the overload relay status. Let's take a look at a representative three-phase overload relay. This one has 3 paired overload elements and 2 auxiliary contacts. The 95 to 96 pair is normally closed. This relay has an adjustable overload setting. If this setting is incorrect, the overload will not function as intended and perhaps trip early, or worse yet, not at all. It has a setting that allows automatic reset after the overload elements have cooled, or another setting, H, think hand, that requires manual reset. Here's a picture of an overload that is not triggered. Notice there is connection between the L1 input and T1 output as indicated by the ohm meter. If I manually test the overload, there still exists a connection from L1 to T1. The overload element in its activated state is not breaking the circuit. If, however, I move my ohm meter to the auxiliary contact, this is where I find an indication of overload. When the overload is not triggered, the 95 to 96 pair of auxiliary contacts is closed. When I manually trigger the overload relay, this normally closed contact opens. This is the interaction point with the control system that indicates it is time to open the contactor. Overload relays are sometimes called thermal overloads or heaters because of their operation mechanism. Although advanced electronic overloads exist, the current-sensitive elements in a typical overload relay are temperature-sensitive devices that heat up when exposed to excess current and open a contact. Current drawn by a motor is a reasonably accurate means of measuring the applied load and thus of its stator winding's temperature. Thermal overload detection mechanisms include a ratcheting pawl, where the geared wheel is held in place with a thermally sensitive solder. When cool, the solder pot is solid and the spring-loaded contact is held closed. If excess current through the heater melts the solder pot, the geared wheel spins and the spring-loaded contact is pushed open, allowing the pilot circuit to de-energize the contactor coil and open the contacts. Here's an example of this mechanism. This is a 3-phase overload relay with only one heater element. When the heater element is removed, we can see the geared wheel. This geared wheel interacts with a spring-loaded contact. When the overload is set, the solid ratcheting pawl keeps the contact closed. However, when subject to high temperatures associated with high current, the solder becomes fluid and lets the wheel spin and opens the contact. Only when the solder pot has cooled and resolidified will the reset engage the pawl with the ratcheting wheel. Another extremely common thermal mechanism is a bimetallic strip around which current-carrying wires are wrapped. The bimetallic strip, as the name implies, is composed of 2 different metals. The 2 different metals expand at different rates. In the ready or go state, the bimetallic strip holds the contact closed. When heated, the 2 metals expand differently and pull the contact open. Here's the internal workings of an overload relay employing this mechanism. These are the bimetallic strips that distort when heated and open the contact. Note that due to the cumulative nature of heat, something commonly called thermal memory, overloads that are previously triggered will trip sooner. Motor damage can occur if the overload relay is repeatedly reset without correcting the cause of the overload event. Ambient temperature can greatly affect tripping time of a thermal overload relay unless it includes some means of compensating for ambient temperature. Thermal detection is not the only means of overload operation. Electronic overload relays use current transformers mounted on each phase that directly measure current. Internal circuitry calculates the temperature based on a user-adjustable setting and will trigger the feedback contact to open in the event of a sustained overload. Advanced electronic overload relays offer other functions in addition to over-temperature detection, including but not limited to instantaneous overcurrent, ground fault, phase loss and unbalance, and over or under voltage protection. Overloads are identified by their class number. The class number indicates how long an overload takes to trip when carrying a current equal to 6 times its current setting. A class 10 relay will trip in 10 seconds or less when carrying current equal to 6 times its rating. A class 20 relay will trip in 20 seconds or less when carrying current equal to 6 times its rating. A class 20 overload relay would be suitable for applications with high inertial load. Manufacturers should supply a graph that shows tripping time as a function of current. As an example, consider an adjustable class 10 overload relay that has been set to 3 amps. The graph shows that it would take around 18-ish seconds to trip if it was carrying 4 times 3 amps or 12 amps. Note the quasi-logarithmic nature of the time axis. Alright, this about wraps up our brief introduction to the overload relay. We'll be making use of this device in later lectures as the means of protecting motors from sustained overload conditions. In conclusion, this lecture took a brief look at the overload relay. We discussed the purpose and function of an overload relay, examined a representative overload relay, discussed the detection mechanism for 2 different types of thermal overloads, briefly discussed the electronic overload relay, and used an overload relay's class number to determine the length of time it takes to trip for different current measurements. Remember to review these concepts and practice these techniques as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.